Good morning, my dear students. We will be continuing the chapter called Magnetism and Matter. And today's topic is torque on a bar magnet which is placed in a uniform magnetic field. It is similar to the torque on an electric dipole which is placed in a uniform electric field. Right? Let's see. There is a uniform magnetic field I have considered here. This is the uniform magnetic field. The magnetic field lines are straight, equally spaced and parallel to each other. So this is the uniform magnetic field B bar. It's a vector quantity, right? So there is a bar magnet which is placed here. Carefully look at this bar magnet which is having a south pole and a north pole. Imagine it's a south pole and it is a north pole here. And the magnetic moment of this magnet will be from south pole to north pole. It is M bar. Alright. So what I can write, it's M bar, it's the magnetic moment of the bar magnet, and B bar is the uniform magnetic field, right? And there is an angle between them, you can see. This is the B bar vector and this is M bar vector and this is called theta. So this theta is the angle between M bar and B bar, remember. Let's talk about the torque before going into the torque. In the last class we have discussed there will be a north pole and south pole here. As the magnetic field lines are moving in this direction, left side of this diagram, you need to imagine or assume there is a huge north pole is available here. And this north pole will definitely repel this north pole of the bar magnet with a force F bar, that is equal to M into B bar. Okay. And this north pole will attract the south pole in this direction with a force same F bar is equal to MB bar. Two equal forces acting in this direction. Alright? Two equal and opposite forces acting on this bar magnet. As two equal and opposite forces are acting on a bar magnet, what I can write, see here, as two equal and opposite forces acting on this given bar magnet, I can say the net force acting on this will be zero. It's called translatory forces, net translatory forces, because in horizontal direction, either towards right side or left side, the system will not move here because these two forces will be zero. The net force of these two will be zero. So that's called the body is in translatory equilibrium. Clear? The body is in translatory equilibrium. But there is a perpendicular distance between these two forces. You can say, if you extend this force, you can see here. So there is a perpendicular distance between these two forces. It is so simple. See the perpendicular distance between these two forces. When there is a perpendicular distance between these two forces, and these two forces we call it as couple, equal and opposite forces. And the perpendicular distance between these two forces is exist. So that, imagine that perpendicular distance I am imagining as x. When this is theta and this also will be the theta, no confusions at all. Alright? And perpendicular distance, why I am concentrating here? Because the torque is equal to force into perpendicular distance between the two forces. What is that force? Force acting on any pole, because both are equal and opposite, right? So why I am talking about the torque? Because the couple is there and there is a distance, perpendicular distance between these two forces is available. Definitely there will be a rotational equilibrium takes place. Translatory equilibrium is zero, right? The body is in translatory equilibrium, but net force is zero, but net torque will never be zero in this case, right? So I'm writing here as, why I have focused on this is as net torque is not equal to zero. The body is not in rotational equilibrium. It is only in the translation equilibrium. So that is the reason I have considered this equation. Torque is equal to force into perpendicular distance. And what is the perpendicular distance here? Let's concentrate on this perpendicular distance topic. So from this triangle, you know, from south pole to north pole. So this is 2L, yes or no? This is called what? Magnetic length. It's not the geometric length, it's a magnetic length. So the hypotenuse of the triangle you have, and you need this opposite side of the triangle. And what is the trigonometric angle you consider? Cos theta? If you take the cos theta, adjacent side by hypotenuse. We don't want the adjacent side. Adjacent side is not the perpendicular distance between the two forces. Opposite side of this triangle is the perpendicular distance between the two forces. And let's say sine theta from the above triangle, it will be x by 2L, and from here x is equal to sine theta into 2L. This you substitute in this, right? So now the torque on this bar magnet will be force which is small m into b, right? Let's write the magnitude, m into b into perpendicular distance. What is the perpendicular distance? It's a sine theta into 2L. Okay, and this you can also write it as how? M into 2L, right, into b into sine theta. What is that small m into 2L? Is it the magnetic moment magnitude? So torque tau is equal to magnetic moment, can be written as a capital M into B into sine theta. You might have done the similar derivation for the torque on an electric dipole when it is placed in a uniform electric field. The similar expression you might have got, and that expression will be like this: tau is equal to Pe sine theta. P is the electric dipole moment, E is electric field. So this is in electricity. No confusion, similar to that. So this is the magnitude. And if you write in terms of vector, as a tau is a vector, so you can write tau bar is equal to m bar cross b bar. Tau bar is equal to what? M bar cross b bar. Okay, clear? That's what the torque. So here, for example, take theta is 0 degrees. So tau will be 0, and if you take theta is 180 degrees, the tau will be 0. If you take theta is 90 degrees, so the tau will be mb. What does it mean? Because sin 90 is 1. So torque is 0 here, 0 here. So in this case, you can say there is a maximum torque will be available at an angle theta degrees. Sorry, 90 degrees. So what is this? In this case, anyhow, in any of the case you take translational equilibrium, the body will be. Net force will be 0, but net torque will not be 0 in all the cases. Net torque will be 0 in this case as well as in this case. In both the cases, net torque will be 0 and net force will be 0, but here net torque will never be 0 in this case when this is the bar magnet is kept in this way. Understand? Clear? Now, two important things you should understand. Number one, two important things you should understand before moving to the further topics. Number one, a direction of the torque. Direction of the torque. You know, by using right hand rule, you'll get it. What is the right hand rule? Simple. Tau bar is equal to m bar cross b bar. Stretch all your right hand fingers in the direction of m bar and curl them towards b bar. You get the torque direction. It's simple. Stretch your right hand palm in this direction. All these stretched fingers must be kept in the direction of m bar and curl them towards b bar. So m bar cross b bar will gives you, that means your thumb will gives you tau bar direction, right? Let's check here. So this is your m bar and b bar is here. See, m bar is here, b bar is here. So m bar and curl towards b bar, and you see the torque is inwards into the plane. That's it. So that's about a direction. And the second important point here is, this is the midpoint. About this point, there will be a rotational effect is produced due to this couple. About this point. Till what time, till what angle the rotational effect will be produced. And let's see. When you keep this in this way, see here, it will be rotated in this way, in this way, and this way, till the time it becomes parallel to this magnetic field. The magnet becomes parallel to the magnetic field, it will be rotated. After that, what happened? After that, the angle between m bar and b bar will become 0 degrees. Then there will be net torque will be 0. That means rotational effect will be 0. Rotational equilibrium the body will be. And anyhow, the body will be in translational equilibrium. So this is the thing called tendency towards the stable equilibrium. Alright? So when you keep the body or a bar magnet placed in a uniform magnetic field, it will have the tendency to move towards a stable equilibrium. What is that? A stable equilibrium. Stable equilibrium means what? Tau is 0 degrees. So I can say this is a stable equilibrium condition. Here only I am telling you, because next topics it will be useful for you. Stable equilibrium condition, and this is called unstable equilibrium condition. I am writing here. So this tau is equal to 0. That means when theta is 180 degrees, so that is called unstable equilibrium. What is this? Unstable equilibrium. About this we will be discussing in the next slide. Okay, so this is the maximum torque will be produced. Questions will be asked in this way, my dear students. On the torque, how the questions will be asked. There will be two types of questions will be asked. Number one, tau is equal to mb sine theta, where it can also be written as magnetic moment can be written as NIA b sine theta. I hope you remember that. Number of turns, current passing through this. A is area vector, so B is magnetic field, and theta is angle between m bar and b bar. So in this way also the torque questions can be asked. The first way, and the second way is the most important thing. A commonly asked question. Second way. Second way is, imagine in case 1 the question is given that torque acting on a bar magnet is maximum. Maximum when it is possible, m into b, that's a maximum, right? Maximum at an angle of 90 degrees. Now the question is, in case 2, at what angle the torque value will be, so simple, will be half of the maximum torque. So simple, right? And what angle? We know tau in this case. Tau in the second case, let's say T dash. T dash is equal to, right? So what is that? Tau maximum by 2. What is T dash? MB sine theta is equal to, now maximum is MB by 2. MB cancel. Sine theta is how much? 1 by 2. So when sine theta is 1 by 2, I can write here sine theta is 1 by 2 and theta value will be how much? 30 degrees. This way questions will be asked. Okay. Clear? Let's solve some more questions and some more topics in this session. I hope you're understanding very well and as maximum as possible in a slow pace we are discussing each and every topic of the chapter. Okay, students, let's continue. Work done in rotating a bar magnet in uniform magnetic field and potential energy stored in it. See, this is a continuation of the previous slide. There is a uniform magnetic field is here. Imagine what we had discussed in the previous slide. There is a bar magnet here having a south pole and north pole and its magnetic moment is in this direction, it's M. And you can also, we have also discussed the angle here. So now what I am going to do here is, it is theta 1, that's called initial angle made by magnetic moment and magnetic field. So the theta 1 is the initial angle. What is the important point I had discussed in the previous slide? According to the torque experienced by this dipole, its tendency will be there to move and comes to the stable equilibrium position. We know that. What is the stable equilibrium position? When theta is 0, right? So theta is equal to 0, so that's called a stable equilibrium position. The tendency, according to the torque, the tendency of this bar magnet to come and align in the direction of B bar. That's called stable equilibrium. For that, you do not need to do some work done. No, it's not at all required. Automatically, it will align in the direction of B bar. You need to do some work done by some external source to move this bar magnet into another angle, that means in the direction away from the stable equilibrium position. I have just taken this bar magnet into some other angle in this way, carefully see. So this is my south pole and north pole. See now the angle here is clearly visible. This is called my theta 2. So theta 2 is the final angle. So simple discussion we are making. There is no difficult concept is involved here. I'm 100% sure. I hope you understood the easiness of the subject. Theta 1 is the angle between M bar and B bar initially. I have taken this bar magnet to the another angle called theta 2 by applying some external source. Okay? Because on its own it cannot move the backwards. It will move towards a stable equilibrium. Now, there is some work done is required, right? So I am writing here, there is some work done is needed to take the bar magnet from initial position to the final position. Initial position to what? Final position. Is it clear? So directly from this theta 1 to theta 2, how much is the work done is required? So that's difficult to find out. So that is why we'll use the formula. A small work done is needed to deflect a small angle theta, d theta. This is the formula from where you got it. In the translatory motion, we know work done is equal to force into displacement. But here it is a rotational motion the body is in. The bar magnet is rotating in this way about this axis of rotation. That's why in rotatory motion, so what is the analog of work done? So W is equal to torque into angular displacement. Previously it was work is equal to force into a linear displacement. Here W is equal to torque into angular displacement. Alright. So in this case, we know dW is equal to tau is mb sine theta into d theta. We don't want dW, right? We need work done needed by an external source to move from theta 1 to theta 2. So for that integration you can make W is equal to integral, what is the angle here? Theta 1 to theta 2 mb sine theta into d theta. Okay, so here, so W is equal to mb will come out here, integral theta 1 to theta 2 sine theta d theta. So this is mp is equal to integral sine theta will be minus cos theta, and this is theta 1 and theta 2 your upper limits and lower limits. Okay, so from here what I can write, W is equal to minus mb, alright, minus mb into cos theta 2 minus cos theta 1. If you substitute or if you multiply this minus inside, you will get it as mb into cos theta 1 minus cos theta 2. Is it okay? So the final answer I am giving you mb into cos theta 1 minus cos theta 2. So this is the formula of work done in rotating a bar magnet in the uniform magnetic field. From what angle to what angle we are rotating. Let's take two important cases here. Imagine your theta 1 is equal to 0 degrees to theta 2 is 180 degrees. According to the physics, in the numericals they will be asking like this. What is the, see, theta 1 is 0 means it's called the stable equilibrium condition. Yes or no? And this is unstable equilibrium condition. Is it clear? Unstable equilibrium condition. The question will be asked, how much is the work done is needed, right, to rotate the bar magnet from stable equilibrium to unstable equilibrium? Understand? So the question can also be reversed. From unstable to stable, right? So what is that? Let's check. W is equal to mb into cos theta 1, it's cos 0 degrees minus cos theta 2, it's cos 180 degrees. Okay. So W is equal to mb into cos 0 degrees is how much? 1 minus cos 180 minus 1, it's 1. Okay. W is equal to 2mb. Understand? Stable to unstable, it will be 2mb. Unstable to stable. Now, from unstable to a stable equilibrium, what is the work done is needed? That you need to do it as a class work. Just pause the video, do that and send me the answer during the class itself. Clear? Understand? So simple, just substitute. Now, in this way questions will be asked. Now what is another topic is potential energy stored in it. When you are doing in this way, there will be a potential energy because work done is always nothing but the energy stored in the body. The amount of work we do is always stored in the form of energy. Here, as the position or the angular displacement is changing, that work done will be converted into the form of energy, which is potential energy. Right? So, according to, I'm saying potential energy, according to the definition, you know, The work potential energy is the work done required, work done needed to displace the bar magnet from the theta 1 is pi by 2 to some angle theta. Theta 2 will be some angle. Understand? So this is called the definition of the potential energy. Potential energy is the work done needed in rotating this bar magnet from this angle to this angle. That's called the potential energy. Let's see, the potential energy U is equal to, work done, right? Okay, U is equal to work done needed to rotate MB into, what is that, cos theta 1? It's cos 90 minus cos some angle theta. Okay, that's it. Cos 90 to some angle theta. Understand? Clear? Now, so this is the formula for the potential energy. Right? So what is cos 90 here? Cos 90 value will be 0. Understand? Cos 90 value will be 0. So from here, I can write U is equal to MB into 0 minus cos theta. So U is equal to minus MB cos theta. As the potential energy is a scalar quantity, so you can write U is equal to M bar. It is minus M bar dot B bar. It's a dot product. Okay. And from here, when theta is equal to 0 degrees, what I can write for theta is 0 degrees, you can write U is equal to minus, cos 0 is 1, minus MB. This is called, carefully see, so theta is 0, means stable equilibrium. At the stable equilibrium, the potential energy is minus MB. So that's called the minimum potential energy. When theta is equal to, here itself, let's write 180 degrees. So U is equal to minus MB into cos 180. Cos 180 is minus 1. Minus into minus, it's plus. So it's plus MB. So this is called the maximum potential energy. And you know, this theta 180 degrees is what? Unstable equilibrium. At unstable equilibrium, the potential energy will be maximum, and the minimum potential energy, it's the body will be in the stable equilibrium. Right? Now, when theta is 90 degrees also you can do it, no problem. Minus MB into cos 90 will be 1, right? So cos 90 will be 0. So potential energy will be 0. Okay. Potential energy will be 0 because our starting position was this 90. This is our starting position. As the initial position, the potential energy is 0. Now, as the position is changing, the potential energy may increase or decrease. Got it? Clear? That's it. Let's look at the given numerical by the students. The potential energy of a bar magnet of a magnetic moment 8 ampere meter square. So given magnetic moment is 8 ampere a meter square, and this is placed in a uniform magnetic field of 2 Tesla. So the magnetic field is given as 2 Tesla. At an angle 120 degrees, we need to find the potential energy. Ready? Potential energy is equal to minus MB cos theta. It's a direct formula. U is equal to minus, M is how much here? 8 into B is 2 into cos 120 degrees. What is cos 120 degrees? Cos 120 degree will be minus 1 by 2. So this U is equal to minus 8 into 2 into minus 1 by 2. 2 gets cancelled. Minus 8 into minus 1 is plus 8 joules. So that is the potential energy in this case. Right? Now the last topic for this session is force between two bar magnets. So most of the topics what we are discussing will not be there for your exclusive PUC exams. The topics we are discussing majorly for NEET syllabus. So it is not like only for the NEET or only for the PUC. So the integrated syllabus we are teaching here, it will be helpful for both PUC as well as NEET. That's the reason we have not even skipped a single derivation. Force between the two bar magnets. In one of the JEE or CET or NEET exams, this question was asked based on this. Two cases will be there. Let's take the first case. A south pole is here, north pole is here. Another magnet of south pole and north pole is here. Till now we have discussed force between two poles of the magnet, right? See, there is a magnetic pole plus M and a magnetic pole minus M at a distance R. So we know the force of interaction between them will be mu naught by 4 pi into M1 into M2, whatever it may be. If it is M1 and it is M2, so M1 into M2 by R square. This is what we have discussed due to the two monopoles. But here, the force of interaction between two magnets, okay, these two magnets are kept at a distance R from their centers. That is the important point. As this is the north pole and south pole, so this north pole will attract the south pole with a force F, and this south pole will attract this north pole with a force F. So it is clearly showing that there is an attraction force between these two. And its magnetic moment directions will be in this way. Clear? Now, there is a south pole and north pole, and here it is north pole and south pole I have considered. Here the magnetic moments are in opposite direction, you see here. Here also the two magnets are kept at a distance R. In this case, north pole will repel this and this north pole also will repel this. Now the force of interaction will be like this. So can I say that the force of interaction is repulsion in this case? So definitely repulsion. Here, in both the cases, the force of interaction will be mu naught by 4 pi into 6 M1 M2 by small r to the power 4. What is M1 and M2? Magnetic moments of these two, and this is M1 and this is M2. This is M1 and this is M2. I hope it's very clear to you. So what you should understand, so M1 M2s will be constant. So this distance you can vary, this we cannot vary, right? So F is inversely proportional to R to the power 4, and from here F1 by F2 can be written as R2 by R1 whole to the power 4. The force of interaction will be inversely proportional to fourth power of the distance between the two magnets. Here we are not going to derive anything here. Just remember the formula. F is equal to mu naught by 4 pi into 6 M1 M2 by R to the power 4. Mu naught by 4 pi value you know, 6 M1 M2 values and R value if you give, you can substitute, you will get the force of interaction between two magnets when they kept horizontally in this way. For example, when the two magnets are kept in this way, south pole and north pole, and this is a south pole and a north pole, magnetic moment directions, you see the magnetic moment directions here, and the distance between the two magnets is R, right? As the directions of magnetic moments M1, M2 are same, right? They repel each other. they repel each other. You need to remember this. And here, south pole and north pole, and south pole, and the magnetic moment directions will be opposite here. As the magnetic moment directions are opposite here, so there will be attraction force exists between these two magnets. Here, the F value will be equal to mu naught by 4 pi into 3 times M1 M2 by R to the power 4. So whatever may be the alignment of the two magnets, so the force of interaction between the magnets will be inversely proportional to R to the power 4 only. Okay, clear? So remember this concept, and most of the times it was asked in these exams. Clear? Get ready for the assignment of your 5 questions. All the very best.